Hello everyone. So, in last class we derived the energy equation. Now, in today's class first we will just summarize what we have done in last class and we will write the governing equations in cylindrical and spherical coordinates. Then we will simplify these equations for Cartesian coordinate for the boundary layer flows. So, you can see we have derived this equation in general, and phi is the dissipation function and mu phi is the dissipation term. Here this is the temporal term, this is the inertia term where temperature is convected due to the velocity v, this is the heat generation per unit volume, and this is the diffusion term. And you can see for laminar incompressible Newtonian fluid flow with constant properties, you can write this equation because constant properties. So, k you can take it outside, and you can see for incompressible flow velocity will be low. So, you can see this term you can neglect, and in general you can write this equation with these assumptions, where dissipation function you can see this is the term you can neglect because for incompressible flow divergence of v will be 0, that means del u by del x plus del b by del y plus del w by del z will be 0. So, dropping this term you can write the dissipation function as this. So, in Cartesian coordinate now let us write the governing equations for laminar incompressible Newtonian fluid flow with constant properties. So, this is the coordinate system Cartesian coordinate x, y, z. So, this is the continuity equation, this is the x component of momentum equation, this is the y component of momentum equation, and this is the z component of momentum equation, where g x, g y, g z are the gravitational acceleration in x, y, z direction respectively, and this is the energy equation and this is the dissipation function. And for these equations you can see you can find the components of viscous stress tensor like this. So, there will be 6 components because this stress tensor is symmetric. So, tau x y is equal to tau y x. So, obviously, we will have total 6 components in the stress tensor. Now, if you use some suitable transformation function, then you can convert these equations in Cartesian coordinate to the equations in cylindrical coordinate. So, if we use this as a cylindrical coordinate, so you can see this is the r and this is the theta and this is the z. Then for r theta z coordinate in cylindrical coordinate, if you use the transformation function as x equal to r cos theta, y is equal to r sin theta and z is equal to z, then you can write the continuity equation as this, r component of equation as this, theta component of equation as this, and z component of momentum equation as this, and corresponding viscous stress tensor will be this. And in spherical coordinate, so we are considering r theta phi. So, this is the phi. So, phi obviously you can see it will vary 0 to 2 pi, this is the theta, it will vary 0 to pi, and this is the r. So, if you use these transformation functions x equal to r sin theta cos phi, y is equal to r sin theta sin phi, and z is equal to r cos theta, then you can write the continuity equation in spherical coordinate like this. This is the r component of momentum equation, this is the theta component of momentum equation, and this is the phi component of momentum equation, where grad square V I is given by this expression, and corresponding components of viscous stress tensor can be written like this. And energy equation now in cylindrical and spherical coordinate you can write like this, and this is the viscous dissipation function, and similarly in spherical coordinate this is the energy equation and this is the viscous dissipation function. Now, we will discuss about the boundary layer flow. We will consider Cartesian coordinate and we will consider external flows. First, we will assume that it is a steady 2-dimensional and laminar flow with constant properties and neglecting dissipation and gravity. So, invoking these assumptions, you can write the governing equations as this. This is the continuity equation, it is a two dimensional flow. So, this is the continuity equation, this is the x component of momentum equation, and this is the y component of momentum equation, and this is the energy equation. And obviously, you can see u is the velocity in x direction, v is the velocity in y direction. So, in today's class we will use boundary layer concept, and we will see that if we can drop some term from these equations for boundary layer flows. So, scientist Prandtl actually used scaling analysis and showed that few terms in the governing equation can be dropped, because those terms are very small compared to the others. So, we will ask these questions now. What are the conditions under which terms in the governing equations can be dropped, and what terms can be dropped? So, these the questions now we will answer one by one. First, let us understand what is boundary layer. Let us consider that you have a external flow over a flat plate. If you see that there will be some region close to the wall where viscous effect is significant, and some other region away from the surface you will find that there is no effect of viscosity. So, you can see here you have a flat plate, let us say of length L, and you have a uniform flow u infinity and temperature T infinity. This velocity is known as free stream velocity, and this temperature is known as free stream temperature. X is measured in the axial direction and y is measured perpendicular to the plate. Now, if you see that the velocity boundary layer, so there is some region where you have effect of viscosity, and this is known as viscous region, and some region away from the surface there will be no effect of viscosity, and that is known as inviscid region. And if you see the velocity profile, obviously to invoke the no slip condition at the wall, velocity will be 0. So, the fluid flow which is residing on the top of this flat plate, the velocity will be 0, and gradually this velocity will increase from 0 to u infinity, where u infinity is the free stream velocity. Now, you can see that there is some region which is known as boundary layer. Inside that you have viscous region, and outside that you will have inviscid region. So, if we consider that this is the edge of the boundary layer, so if we consider that this is the edge of boundary layer, then you can see this distance from the normal distance from the flat plate is known as hydrodynamic boundary layer thickness, that is denoted by delta. Delta is the normal distance from the plate at which this velocity u becomes almost 99% of u infinity. So, that is known as hydrodynamic boundary layer thickness, and this fictitious line where at every x distance you have the hydrodynamic boundary layer thickness. So, that is known as edge of boundary layer. So, the inside this edge of boundary layer you can see there is a viscous region, and outside it is inviscid region. So, you can see under certain conditions the action of viscosity is confined to a thin region near the surface is called the hydrodynamic or velocity boundary layer. Now, if you consider the thermal part, so you can see you have free stream temperature T infinity, and let us say wall temperature is Tw and Tw is greater than T infinity. Okay. Then you can see that there will be some region where thermal effect will be there and temperature gradient will exist, and this temperature will vary inside this layer from Tw to T infinity, and outside this region you can see it will maintain the free stream temperature T infinity. So, the normal distance from the plate up to which you have the effect of this temperature gradient, so that is known as thermal boundary layer thickness and denoted as delta T. So, you can see that this fictitious line, inside there is a temperature gradient, but outside you have free stream temperature T infinity. So, this is the edge of thermal boundary layer. So, you can see under certain conditions thermal interactions between moving fluid and a surface is confined to a thin region near the surface called the thermal or temperature boundary layer. So, here we have to consider two important assumptions. One is that there is no flow separation. Okay. Then under that condition we can derive the boundary layer equations, and you have a slender body, that means thickness of the body is much smaller than the length of the body. So, you can see conditions for hydrodynamic boundary layer, you have slender body without flow separation, and we have to consider high Reynolds number flows, and Reynolds number should be greater than 100. Conditions for thermal boundary layer, slender body without flow separation and high Reynolds and Prandtl numbers flow, that means the Peclet number, which is the product of Reynolds number and Prandtl number, should be greater than 100, and you can see Peclet number you can write in this expression. So, you can see that Peclet number is the ratio of the heat transferred by the convection to the heat transferred by conduction. So, let us list down the observations of this boundary layer flow. Fluid velocity at surface vanishes, rapid changes across boundary layer to u infinity. So, from 0 to u infinity this change is occurring inside the boundary layer. Rapid changes temperature across boundary layer from Tw to T infinity. So, you can see it is changing from Tw to T infinity inside the thermal boundary layer. Another observation is that boundary layers are thin. From the experiment it is seen that for air at 10 meter per second parallel to 1 meter long plate, this boundary layer thickness will be of the order of 6 millimeter at the end. Okay. At x equal to 1 meter you will get 6 millimeter. So, you can see that you have the length of the plate as 1 meter and the boundary layer thickness is 6 millimeter. So, it is very small compared to the length of the plate. So, you can see boundary layers are very thin. Viscosity plays negligible role outside the viscous boundary layer, which is your inviscid region, and boundary layer exists in both forced and free convection flows. Now, we will use two different approaches to see that which term we can drop from the governing equations. So, first let us use the intuitive arguments. So, you can see that in the right hand side of the momentum equations we have viscous terms. Let us see that if we can drop one term. So, there are two viscous terms, okay, del 2 u by del x square plus del 2 u by del y square. So, this is not conduction, this is diffusion or viscous. Okay. So, these are the two terms. Now, let us consider one small insect which is sitting inside the boundary layer and it is not disturbing the flow, and let us say that it is flying at this position 0. Now, it is experiencing a high velocity and it wants to shift to a lower velocity region. So, by intuitive arguments what can you say that where it will go 1, 2, 3 or 4 positions. So, you can see obviously that it will travel to position 4 because it will have less velocity, right, because if it is travels from 0 to 4 then it will have less velocity, and if it ultimately goes to the surface then it will not feel any velocity. So, you can see that changes in u with respect to y are more pronounced than changes with respect to x. So, it does not answer that the change of this gradient del u by del x is which one is smaller than the other. Now, you see that the insect is just one step away from the surface. So, you can see that if it goes to the surface then obviously the velocity will become 0 and the changes in the velocity gradient will be more. If you consider that insect is at the edge of the boundary layer and if it is goes away from the surface, then you will find that there will be not much variation in the velocity, right, or velocity gradient. And if you consider in the axial direction, if it moves then obviously there will be not much change in the velocity gradient. So, that means that your velocity gradient with respect to y is much higher than the velocity gradient with respect to x. So, considering that, you can see that del 2 u by del x square will be much less than del 2 u by del y square, and you can drop the term del 2 u by del x square from the momentum equation. So, now what about the pressure terms? Okay. So, if you consider slender body, so obviously streamlines are nearly parallel and you will have very small vertical velocity. So, if you have very small vertical velocity and if you consider the y momentum equations, then all the inertia terms and viscous terms will become 0. So, you can consider that the pressure gradient del p by del y will be almost 0, very small. So, obviously del p by del y will be close to 0. So, you can write p is only function of x and del p by del x you can write as dp by dx, and as pressure gradient along the y direction almost 0, whatever pressure is there outside the boundary layer p infinity, so that will also be impressed inside the boundary layer because there is no change in the pressure in y direction. So, whatever pressure is there p infinity here, so inside also at this x location will be same pressure everywhere. So, you can see that you can write dp by dx is equal to dp infinity by dx, and since p infinity is the pressure at the edge of the boundary layer, that means at y is equal to delta, it can be independently obtained from the solution to the governing equation for inviscid flow outside the boundary layer. So, you can see that in the momentum equation then we can write del p by del x is equal to dp infinity by dx. So, we have these boundary layer equations, this is the continuity equation, and del p by del x we have written dp infinity by dx, and dropping the term del 2 u by del x square, this is the term we have written. So, now you can see that if you divide by rho then you can write in the right hand side minus 1 by rho dp infinity by dx, and mu by rho is your kinematic viscosity. So, nu del 2 u by del y square. Now, let us use another approach which is your mathematical approach, that is your scale analysis. So, here we will use the order of magnitude analysis and we will see the order of magnitude of each term in the governing equations and which term is having less order of magnitude compared to the other will drop from the governing equations. So, use scaling to arrive at boundary layer approximations, assign a scale to each term in the equation. So, obviously, we have free stream velocity u infinity, length of the plate as L, and hydrodynamic boundary layer thickness delta. Okay. Now, we will postulate that delta by L is much smaller than 1, because we have already seen that for air at 10 meter per second parallel to 1 meter long plate, delta is of the order of 6 millimeter at the end. So, obviously, we can assume that delta by L is much smaller than 1. Now, let us answer these questions. What terms in the governing equation can be dropped? Is normal pressure gradient negligible compared to the axial pressure gradient, and under what conditions is delta by L much smaller than 1 valid? So, we will answer these questions one by one. So, first assign the scales. So, velocity scale, you can see the free stream velocity is u infinity. So, we can assign the scale for this velocity u as u infinity. We have hydrodynamic boundary layer thickness delta. So, in y direction, so obviously y we can write as order of delta, and length of the plate is L. So, the order of x we can write as L. Now, let us consider the continuity equation and find what is the order of velocity v. So, this is the continuity equation. So, you can see del v by del y you can write as order of del u by del x. Okay. So, you can write the order of v as this is the del u by del x. So, what is the order of u? It is u infinity. What is the order of delta y? This is delta and divided by x. So, you can see the order of velocity v is u infinity delta by L. So, here you can see we have already assumed that delta by L is much smaller than 1. So, you can see v will be much smaller than u infinity. Okay. So, the velocity in y direction v is very small, okay, compared to u infinity, and we got the scale for v velocity as this. Now, let us answer this question: what terms in the governing equations can be dropped? So, we have already assigned the scales and we have found the scale for velocity v. So, you can see this is the u scale, this is the v scale, this is the y scale, sorry, this is the y scale is delta, and this is the x scale L. Now, let us consider the convection terms. So, del u del u by del x plus v del u by del y. So, first term is u del u by del x. Okay. So, what is the order? U is u infinity, this is your u infinity, and this is L. So, that means u infinity square by L. Now, consider the other convection term v del u by del y. So, what is the order of v? You see, this is your u infinity delta by L, and u is u infinity and y is delta. So, you see this is u infinity square by L. So, you can see both are of same order. So, you cannot drop any terms. So, the two inertia terms are of the same magnitude. So, we cannot drop any term in the convection terms. Now, let us consider the viscous terms. Okay. So, we have del 2 u by del x square. So, you can see this is the order of u infinity divided by L square, and you have del 2 u by del y square is order of u infinity by delta square. Okay. So, now you can see that we can write del 2 u by del x square divided by del 2 u by del y square. So, this ratio will be order of u infinity by L square divided by u infinity divided by delta square. So, you can see you can write this as order of delta by L whole square. So, we have already assumed that delta by L is much smaller than 1. So, from here you can see that del 2 u by del x square will be much smaller than del 2 u by del y square. So, as delta by L is much smaller than 1. So, del 2 u by delta x square will be much smaller than del 2 u by del y square. So, del 2 u by del x square can be neglected from the viscous terms. So, you can see that if delta by L is much smaller than 1, then you can drop the term del 2 u by del x square. So, dropping the del 2 u by del x square term, you can write the x component momentum equation as this, and following the same procedure you can drop del 2 v by del x square from the y momentum equation, and you can write like this. Now, the next question is that is normal pressure gradient negligible compared to the pressure gradient. So, next question is that is normal pressure gradient negligible compared to axial pressure gradient. So, now you can see that in the u momentum equation we have the term del p by del x, and in the v momentum equation we have del p by del y. Now, let us consider these each pressure gradient term with corresponding inertia term. Okay. So, in the u momentum equation compare this term with the inertia term, and v momentum equation compare this pressure gradient term with the inertia term, because both terms are of the same order we have already seen. So, you can take any one term. So, you can see that del p by del x, okay, will be order of rho u del u by del x, right. So, you can see del p by del x will be rho u infinity, this is u infinity divided by x length is L. Okay. So, this is rho u infinity square by L. Now, if you see the pressure gradient term in the y component of momentum equation, so you can write del p by del y will be order of rho u del v by del x. Okay. So, del p by del y will be rho u infinity, and v is the order of u infinity delta by L. So, u infinity delta by L and 1 by L. Okay. So, del p by del y you can write order of rho u infinity square delta by L square. Okay. So, now see the ratio del p by del y divided by del p by del x. Okay. So, this is the order of, so del p by del y is this one, rho u infinity square delta divided by L square and divided by del p by del x. So, it is rho u infinity square by L. So, you can see this will be order of delta by L. Okay. So, from here you can see that delta by L we have assumed as much smaller than 1. So, obviously, your del p by del y will be much smaller than del p by del x. Okay. So, you can see as delta by L is much smaller than 1. So, obviously, del p by del y will be much smaller than del p by del x. So, you can see that del p by del y will be order of 0, because it is very small. You can see that we have done the balance between the pressure gradient and the inertia term. You can also balance the pressure gradient with the viscous term, and you will get the same result. Okay. So, now you can see for the 2-dimensional flow P is function of x and y. Okay. So, for 2D flow we know that P is function of x and y. So, you can write dP is equal to del p by del x dx plus del p by del y dy. Now, you can write dP by dx. Okay. So, we have divided by dx. So, you can write del p by del x, and if you take common then you will get 1 plus. So, you can write del p by del y divided by del p by del x, because del p by del x we have taken outside, and we have also taken divided by dx. So, dy by dx. Okay. So, now you can see what is the order of dy by dx. dy by dx is order of y is delta and x is L, and del p by del y and the ratio of del p by del y to the del p by del x, that also we have derived in the last slide as delta by L. So, you can see dp by dx you can write del p by del x 1 plus delta by L whole square, because dy by dx is order of delta by L and del p by del y also will be delta by L. So, you can write this as order of this. So, as delta by L is much smaller than 1. So, you can write dp by dx is equal to of the order of del p by del x. Okay. So, now you can see that the in the as del p by del y is negligible, so p is function of x only. Okay. So, now at a given location x, the pressure P x inside the boundary layer is the same as the pressure P infinity at the edge of the boundary layer y is equal to delta. So, if you can see that outside the velocity boundary layer, if you have a pressure gradient P infinity, okay, which is function of x, then P x will be equal to P infinity x, okay, and del P by del x will be order of dP infinity by dx, and in the u momentum equation you can see that it will become u del u by del x plus v del u by del y is equal to minus 1 by rho, the pressure gradient term now you can write as dP infinity by dx plus nu del 2u by del x square. So, this is the boundary layer equation. What about the v momentum equations? So, you have seen that v is much smaller than u infinity, right, and it is having very small value, and from there we have derived that del p by del y also is very small value. So, in the y momentum equation if you see all the terms will be order of delta. Okay. So, you can neglect the y momentum equation. So, in y momentum equation each term is of order delta. So, all terms in this equation are neglected, leading to the important boundary layer simplifications of negligible pressure gradient in the y direction. So, now you can see that these equation we have derived in general, okay, where p may be function of x, okay, and the as del p by del y is 0. So, obviously, the pressure at the outside the boundary layer will be also function of x. So, you can see that p infinity is function of x. So, that can be impressed inside the boundary layer and it will have at a certain x location it will have the same pressure. Okay. Now, this pressure gradient if you consider for a, let us say you have a in general curved surface and you can have the boundary layer like this, where this is the boundary layer thickness delta and x is measured along the surface and y is measured perpendicular to the surface. In this particular case actually you will get that outside pressure P infinity will be function of x, and for that reason your velocity, free stream velocity u infinity will be function of x. So, you can see that for this particular case from this equation if you apply outside the boundary layer then what will happen? Okay. So, obviously, you can see that from here you can write u infinity then del u by del x. So, it will be u is function of x only. So, you can write du infinity by dx and v is very small, negligible. So, you can drop this term is equal to minus 1 by rho dP infinity by dx, and obviously outside the boundary layer u is function of x only. So, del 2 u by del y square will be 0. So, you will get this equation. So, you can see 1 minus 1 by rho dP infinity by dx you can substitute with u infinity into du infinity by dx. So, if you write it here then you can get, so you can write it here u del u by del x plus v del u by del y is equal to, now you can substitute it here. So, u infinity du infinity by dx plus nu del 2 u by del y square, okay, where u infinity is function of x. And if you integrate this equation, what you will get? If you integrate this equation, you can see you will get p infinity plus half rho u infinity square is equal to constant, okay, and it is valid in the inviscid region outside the boundary layer, okay, inviscid region. Now, if you consider a special case, that flow over flat plate, okay. So, in case of flow over flat plate, this u infinity will be constant, it is not function of x. So, for flow over flat plate, u infinity is constant. So, here you can see that if u infinity is constant, then du infinity by dx will be 0, because u infinity is constant. So, du infinity by dx will be 0. So, if you have a flow over flat plate where u infinity is constant, okay, then you can write your boundary layer equation as u del u by del x plus v del u by del y is equal to nu del 2 u by del y square, okay. So, that means your dp infinity by dx will be 0, okay. So, you can write this equation as a special case for flow over flat plate, okay. But if it is a curved surface like wedge or flow over a cylinder, then you have a curved surface, then in that case your u infinity is function of x and you have to consider the pressure gradient term dp infinity by dx in the momentum equation. Now, the last question is that under what conditions is delta by L much smaller than 1 valid, okay. So, let us answer this question. So, what we will do now? Now, you can see in the left hand side the inertia terms are of the same order, okay. So, we will take one inertia term and we will compare it with the viscous term, because we have only one viscous term, right, nu del 2 u by del y square. So, this will compare. So, you can see u del u by del x, one inertia term will compare with the viscous term del 2 u by del y square, okay. So, what is the scale? So, u is u infinity, this is your u infinity, x is L nu u infinity by delta square. So, if you take delta square in the left hand side, if you divide both sides by L, then you will get L square, then you can see here you will get nu by u infinity L, and we can define Reynolds number based on free stream velocity infinity and plate length L, then we can write R e L is equal to u infinity L by nu. So, you can see from here it will be 1 by R e L and delta by L will be order of root R e L. Now, we will answer this question. So, if delta by L is much smaller than 1, so what will be this term? So, if delta by L is much smaller than 1, then the root R e L will be much greater than 1, okay. So, you can see that it is a high Reynolds number flow. So, if you have high Reynolds number flow, but not in the range of turbulent, okay, then you will get the hydrodynamic boundary layer thickness is very small compared to the length of the plate. So, if you consider Reynolds number 100, then let us see that what is the delta by L order. So, if consider R e L as 100, then you can see from here delta by L will be order of, so it will be 100, so root 100 is 10, so it will be 0.1. So, you can see that it is very small. So, generally we say that these equations are valid when Reynolds number is greater than 100, okay. Now, for any length x, this expression you can write as delta by x is order of 1 by root Rex, where the Reynolds number based on x we have defined as u infinity x by nu. Okay. Now, let us find what is the wall shear stress and the friction coefficient. Okay. So, what is the order of these terms? So, now we know that for two dimensional flow, wall shear stress tau w is mu del u by del y. So, for 2D flow we know tau w is equal to mu del u by del y. So, you can see that tau w will be order of mu u infinity and y is delta. Okay. And we know that delta by x as 1 by root r e x. So, tau w will be order of mu u infinity by x, x by delta. So, you can write mu u infinity by x and x by delta is r e x to the power half. And we know that friction coefficient C f is tau w by half rho infinity square. So, you can see that friction coefficient C f will be generally tau w by half rho infinity square. So, if you see the order of C f will be tau w by rho infinity square. Okay. We will not consider half because we are doing the order of magnitude analysis. Okay. So, you can see that C f. So, tau w will be mu u infinity by x r e x to the power half, okay, and 1 by rho u infinity square. So, if you see from here that if you rearrange, C f will be order of mu by rho u infinity x r e x to the power half, and C f will be, so this is your 1 by r e x, okay, r e x to the power half. So, if you see that C f will be order of 1 by root r e x. Okay. So, if 1 by root r e x and delta by x is also 1 by root r e x. So, obviously, you can see C f is order of delta by x, right, of the order of root r e x. So, let us summarize what we have studied in today's class. So, first we have just written the governing equations in Cartesian, cylindrical and spherical coordinates. Then we considered external flow and we have discussed about boundary layer. So, we have seen that near to the wall we have a small region where you have a effect of viscosity. So, that is known as viscous region, and outside this and away from the surface there is a region that is known as inviscid region where there is no effect of viscosity. Then we used intuitive arguments and scale analysis and we have derived the boundary layer equations. So, you can see this is the continuity equation and this is the momentum equation we have derived expressing the term P as P infinity, because from y momentum equation we have seen that del P by del y is order of 0. So, this is the equation we have seen, and as a special case also we have discussed that if you have a flow over flat plate then u infinity is constant and there will be no axial pressure gradient. Okay. So, there will be dP infinity by dx will be 0. Okay. So, this term you can drop for flow over flat plate. Then we have derived this relation delta by L is order of 1 by root R E L, and if delta by L is much smaller than 1, obviously it has to be a high Reynolds number flow. And for any x we have written delta by x as this expression, and from here we have written the shear stress as order of mu infinity by delta and we got this expression. And then we have seen that your friction coefficient is order of delta by x and C f will be 1 by root R E x. Thank you.